Angela, so we've been given a set of averages for a particular climate zone in Australia. Could you show me how you could plot that particular climate zone on our psychrometric chart?
Sure. So to start off with, we take the T-min temperature, which is 13.6 degrees, which is around about here. And then we also take the relative humidity at 9 a.m., which is 66%, which if we follow down, it comes to about here. So we put our first point there. And then we take our T-max temp, which is 28.5 degrees, which is approximately here. And then we also take the relative humidity at 3 p.m., which is 35%. So if that's 50%, 40%, 30%, and then we go up to about here. So that's our second point. And then we want to join these two with a straight line like that.
All right, thank you, Angela. So one thing with this particular diagram is that each of these lines describe a monthly. So these temperatures and these averages are obviously mean maximum temperatures for each month averaged, and of course the same for the relative humidities. So when you go through and you actually plot this on your diagram, it's not going to be exactly what we have here, but you will have something of the same form. Okay, so we've now plotted our climate zone on our psychrometric chart from our average values. We now want to look at how we can plot the comfort zone, the thermal comfort zone, on this psychrometric chart. Angela, could you show me how you begin plotting the comfort zone?
Sure. So to start off with, we need to find Tn, which is the temperature of neutrality. And from that, we find the lower and upper temperatures of the thermal comfort box. And we plot that on the 50% relative humidity line. But to start off with, we need to find Tn. So to find Tn, we use an empirical formula, which is given by Tn is equal to 17.6 plus 0.31 times the dBT average. And the dBT average, that comes from these two values here, which is Tmax minus Tmin divided by 2, which is the average. So to get this, we do 20 plus 7.1 over 2. And you can just put that into a calculator straight away, subbing that in, and you can get Tn is equal to 21.92 degrees Celsius. And using that, you can find your upper and lower limits. So if the question asks for an annual thermal comfort box, you use plus or minus 2, which is what we're going to use. But if it asked you for monthly, you'd use plus or minus 1.75 from this value here. So to find the upper, we do 21.92 plus 2 degrees, which is going to give us 23.92 degrees Celsius. And to find the lower one, we need to do 21.92 minus 2 degrees, which is going to give us 19.92 degrees Celsius. So now that we have these values, we can plot them onto the 50% relative humidity line. So to start off with, we have 23.92, which is approximately around here. And we want to put that onto the 50% relative humidity line. So that is our upper. And then for our lower, we have 19.92, which is approximately here. We want to put that on the 50% relative humidity line. So that's about here.
So we've now found the upper and lower bounds of our thermal comfort box. So what we now have to do is find out where we're actually intersecting on the diagram to actually draw our box. So we're looking to draw our set lines. Those are our standard effective temperature lines. So these describe the change in effective temperature with relative humidity. So these lines are going to go through our lower points and upper points and intersect on the x-axis somewhere. These are arbitrary at the moment, so I haven't drawn them in exact because we haven't calculated them. But just to illustrate, somewhere they'll intersect on the diagram. So Angela, can you show me how we calculate the intersection for these set lines?
Sure. So to do that, you're going to need to use an empirical formula, which is given by delta dBT over delta omega equal to minus 0.025 multiplied by dBT minus 14. just to explain what these terms actually are. So the delta dBT is the difference between your dry bulb temperature, which will either be from your L or your U. For the moment, we're just focusing on L, so we'll use L, and where this set line intersects with the x-axis. And your delta omega will come from the psychrometric chart. So for L, you come across here and you find what this absolute humidity value is. It so happens to be that this value is 0.0071, but for this formula you need it in grams, not kilograms, so we'll be using 7.1. So to start off with, we need to rearrange this. So we will start by doing delta dBT is equal to negative 0.025, but we know that this value here has to be negative, so that negative will turn into a positive, multiplied by dBT minus 14 times by delta omega. Now that we have this equation, we can simplify it even further. So we know that our delta dBT is the difference between here, so we will do XL minus L, which is this what we found before, is equal to 0.025 multiplied by dBT, which is our L again, minus 14 by our delta omega, which we found before was 7.1, remembering that we need grams, not kilograms. So to get XL, we move L over the other side, and we get plus 0.025 multiplied by L minus 14 times by 7.1. And from before, we know that our L value was 19.92, so we sub that into this equation to find what our x-intercept for this point set line is. And we get that our value for XL is 20.9 degrees Celsius. So once we have that, we can plot it onto here. So 20.9 is approximately here. This line was arbitrary before, but now we're going to draw in the correct one. So we go through this point and through this point here to get something that looks something like that. And then for U, we do a very, very similar calculation, except wherever we've had an L, we now put a U. So for instance, here we would have XU minus U times this, and our omega W will come from the U. So we come across here, and it will turn out to be something like 0.0095, but again, we want grams, not kilograms. So if you put it through the calculation, you'll get that your XU value is equal to 26.27 degrees Celsius. So you'll come over here, plot it on here, it's around about here, and then draw that line. So once we have those, we can complete our box by putting in the set lines. So we have a line coming through here from 0.012, which will be the top of our box. And we also have a line that comes from the 0.004, which will be the bottom of our box.
Excellent. Okay, so that is our thermal comfort region here. Thank you. Right, so we're looking at the solar temperature. So we're looking to calculate the solar temperature for this particular opaque surface on the building for this particular setup that we have. So if we look back, we know that the solar temperature, if we look back at our diagram in our lectures, the solar temperature is our instantaneous excess temperature on top of the outdoor temperature. So that is caused by radiation on the surface of your wall. So Angela, can I get you to calculate for me the solar air temperature and the additional heat gained as a result of that solar air temperature to this opaque element of a building?
Sure. So to find the solar air temperature, we use this equation. So solar air temperature is equal to the outside air temperature plus the excess solar air temperature, which is given by G, which is irradiance, alpha, which is absorptivity, RSO, which is the outside air film. So we know what the outside air temperature is. That's given to us in the question. That's 18 degrees C. And we also know what a radiance is. That's also given to us. That's 800 watts per meter squared. We're given absorptivity, which is 0.4. That's dimensionless. And we're also given the outside air resistance, film resistance, which is 0.04 meters squared Kelvin per watt. So the interesting part is that the 2 watts cancel out, and that should be meters squared. The meters squared cancel out. So we end up with adding degrees Celsius with Kelvin, and as you know, per degree Celsius and per Kelvin are the same. So 18 plus the salt air excess temperature is calculated to be 12.8 degrees. So that ends up being 30.8 degrees C. And then now that we have this, we can find the additional heat transfer through the wall. So to do the additional heat transfer through the wall, we use this value here. And as always, the heat transfer through a wall is given by Q is equal to UA delta T. U is given to us in the question, U wall. A is the area of the wall, which is also given to us, and the delta T is just this value here, which we calculated before. So if we put that into the equation, we get 1.47 watts per meters squared Kelvin multiplied by 12 meters squared times by our difference in temperature, which as before is from here, 12.8 degrees C. We have some cancelling of units going on. So the meters squared and the meters squared and the Kelvin and the degree C go. And we end up with a value that is 226 watts. So the additional heat transfer to the wall because of the excess solar air temperature is 226 watts.
Excellent.